Imagine waking to this: 7 billion gallons of water appearing from nowhere inside California's most critical reservoir. No rain falling, no upstream releases occurring, every explanation failing. In this scenario, sensors at Lake Oroville begin screaming alarms into the darkness at 2:17 a.m. Within 4 hours, the water level surges 23 feet higher than any model predicts. The shoreline creeps 60 feet inland, swallowing docks, submerging benches, and erasing landmarks that have stood for decades. What geological force could inject this volume of water from below? Why did seismic monitors detect tremors at the exact moment the surge began? And if the dam was engineered only for surface inflows, what happens when billions of gallons enter through the lake bed itself? The technicians who first notice the anomaly assume their instruments have malfunctioned. They check the primary gauges, then the backups. The numbers match perfectly. Manual measurements confirm what seems impossible. Water appears to be entering the lake from somewhere underground. But this would only be the first warning. In such a scenario, the Eastern Basin would tell a story defying every textbook. Field crews arriving at dawn would find the intake tower now kissed by wavelets that should be 20 feet below. Buoys drifted inland, concrete benches installed during the 2021 drought, a historically verified low water period when the lake dropped to just 22% capacity, now sit completely submerged. Investigators would eliminate explanations one by one. Radar showing crystal clear skies across the Sierra Nevada watershed. Upstream reservoirs at New Bullard's Bar and Antelope Lake reporting perfectly stable levels. Satellite imagery revealing no landslides, debris flows, or visible displacement anywhere in the Feather River drainage. Surface hydrology unable to account for the surge. The conclusion would seem inescapable. Something beneath the lakebed had opened a pathway to a reservoir no engineer knew existed. The volume involved would suggest a source of almost unimaginable scale, pressing upward through fractured rock. Every scientific principle suggests this should not happen. Every hydrological model insists water flows downhill, not up through solid earth. Yet geological research has documented cases where pressurized deep aquifers can force water upward through fault systems, a phenomenon that could theoretically occur beneath any major reservoir. And in this scenario, the water keeps rising. Lake Oroville is not an ordinary reservoir. It is the single most important storage facility in the California State Water Project, holding 3.54 acre-feet of water when full. This represents 61% of the entire SWP system capacity. More than 27 million Californians depend on its flows for drinking water, irrigation, and industrial use. The dam itself stands 770 feet high, making it the tallest in the United States, 43 feet taller than Hoover Dam. Its hydroelectric complex generates enough power for approximately 800,000 homes. During dry seasons, carefully managed releases from Oroville travel hundreds of miles through the Sacramento-San Joaquin Delta, sustaining farms across the Central Valley and cities throughout Southern California. A single point failure here would cascade through the state's entire water infrastructure. The consequences would reach from San Diego to the Bay Area within days. This is why unexplained behavior at Oroville triggers statewide concern. What came next shocked even the scientists. Every resident of the Feather River corridor carries a specific trauma, and this is documented fact. On February 7, 2017, operators discovered a massive crater had opened in the main spillway during routine flood releases. Within days, as rain continued and inflows exceeded 250,000 cubic feet per second, water began pouring over the emergency spillway for the first time in the dam's 49-year history. The hillside beneath that emergency spillway began eroding far faster than anyone anticipated. Headward erosion threatened to undermine the concrete weir at the top. Officials warned that failure could send a 30-foot wall of water crashing into downstream communities. In the largest dam evacuation in American history, 188,000 people fled their homes in Butte, Yuba, and Sutter counties on February 12, 2017. The crisis ultimately cost over $1 billion to repair. Independent forensic teams concluded the incident resulted from a long-term systemic failure to recognize inherent design weaknesses and deteriorated conditions. Now, less than a decade later, sirens are again potential trauma triggers for survivors. The sound of alarms carries different weight in communities that once watched the nation's tallest dam nearly collapse. Trust was shattered in 2017. It has never fully healed. The signs would already be spreading. In such an emergency, the California Department of Water Resources would activate protocols requiring chain of custody water samples from multiple depths. Independent laboratories would search for anything unusual in the chemistry. Based on established geochemistry research, water rising from deep crustal sources would carry distinctive signatures. Elevated lithium and boron concentrations are well-documented markers of geothermal systems and deep formation waters, according to studies published in journals like Geochemistry, Geophysics, Geosystems. Trace rare earth elements would appear in ratios characteristic of water that had spent millennia migrating through hot, pressurized rock. Oxygen isotope analysis, a standard technique for determining water origins, could reveal whether the isotopic signature matched Sierra Nevada precipitation or something far older. Mineral compositions formed under sustained heat and pressure would point to deep underground origins. If such signatures appeared at Oroville, it would suggest the water had not fallen from the sky recently. It would have risen from somewhere far below. But the ground could hold one more secret. In a scenario like this, seismologists reviewing continuous monitoring data might discover something initially seeming coincidental: a swarm of microquakes rippling beneath the basin, tremors too small to feel, magnitudes between 0.8 and 1.4, but with timing impossible to ignore. Geological surveys have long mapped fault systems threading beneath the Oroville region. Research on fault-controlled fluid migration suggests that under the right pressure differentials, even microscopic widening of fractures can permit massive water flow. Studies of deep aquifer systems worldwide show that crack expansions measured in millimeters can transmit thousands of cubic feet per second when connected to pressurized sources. If such correlation between tremor timing and water arrival occurred, it could suggest microquakes had opened conduits. Something underground would be forcing its way up, and the evidence would be building. Engineers face a threat that terrifies them more than earthquakes or floods. Internal erosion, known as piping, occurs when water seeps through an earthen dam and begins carrying soil particles with it. The process starts invisibly. Microscopic channels form. Each particle removed widens the pathway for more water. The cycle accelerates until catastrophic failure becomes inevitable. According to the International Commission on Large Dams, internal erosion causes approximately 50% of all embankment dam failures worldwide. The Association of State Dam Safety Officials describes piping as particularly dangerous because external evidence may be subtle or entirely absent until hours before collapse. The Teton Dam in Idaho demonstrated this horror on June 5, 1976. Workers noticed muddy seepage at 7:30 a.m. that Saturday morning. By 11:55 a.m., the dam had catastrophically failed, releasing approximately 80 billion gallons and killing 11 people. The 305-foot dam was filling for the first time when permeable foundation materials and fractured rhyolite in the abutments allowed water to migrate through the structure, eroding soil until the embankment collapsed. Oroville is an earthfill dam built on Sierra Nevada foothills geology. The parallels would not be lost on anyone monitoring an unexplained water surge. In a scenario involving mysterious water intrusion, troubling indicators could emerge. Drainage discharge downstream might show unusual cloudiness, suggesting sediment transport that should not occur under normal conditions. Pressure sensors embedded in the structure could return values outside their historical range. Based on what we know about the 2017 crisis, certain readings might echo patterns observed in the months before that near catastrophe. history warns that such signals demand immediate attention. Consider a family on the front line of such an event, a longtime resident of Pine Ridge Road overlooking the eastern shore, someone who remembers the terror of 2017, the midnight phone calls, the headlights streaming south on Highway 70, someone who swore never to be caught unprepared again. On the morning after such a surge, they would walk to their usual overlook and freeze. The shoreline would have moved. Landmarks used for decades to judge lake levels would be underwater. Trees that normally stood 20 feet from the waterline would have waves lapping at their trunks. They would not wait for evacuation orders. Within hours, bags would be packed, documents secured, vehicles loaded. They would leave for relatives elsewhere, choosing self-evacuation over official uncertainty. "We watched the spillway nearly kill this town once," such a resident might say quietly. "I will not watch it again from a rooftop." Across the region, others would make similar calculations. Submerged docks and mudslide-covered access roads could isolate neighborhoods. The infrastructure people rely on for escape might disappear beneath rising water. Environmental scientists would warn of cascading ecological damage. Rapid water level changes are known to increase turbidity, which research shows can suffocate salmon spawning beds. The Feather River Fish Hatchery, which supports fisheries accounting for an estimated 20% of ocean sport and commercial catches in the Pacific, would face disruption. Sediment disturbance could resuspend heavy metals that settle in reservoir lakebeds over decades, potentially contaminating the food chain. The situation would deteriorate faster than anyone could respond. As night falls in this scenario, the lake behaves strangely. Despite calm air, whitecaps appear across the surface. Additional rise is recorded between sunset and midnight. The water churns and swirls in patterns suggesting turbulence far below, as though something continues feeding the surge from underneath. Then the dam begins to sing. Technicians monitoring acoustic sensors detect high-frequency emissions emanating from within the structure. Research published in engineering journals confirms that stressed structures emit acoustic signals, sounds that pulse rhythmically as materials adjust under changed loading conditions. Such emissions could indicate the dam is being subjected to forces its designers never anticipated. Oroville Dam was engineered exclusively for surface inflows. Every calculation, every safety margin, every stress analysis assumed water would enter only through the Feather River tributaries flowing in from above. No precedent exists in dam engineering literature for massive bottom-fed injection from deep aquifers. No historical case study describes how an earthfill embankment responds when pressure builds simultaneously from above and below. The engineering manuals would offer no guidance. The dam would be operating beyond its design limits. Every safety factor calculated by its builders assumed a world where water obeyed predictable rules. Data processing required to analyze emergency monitoring would take weeks. Meanwhile, lake levels would continue climbing. Engineers would find themselves racing against physics, trying to understand a phenomenon the textbooks said was impossible, while that phenomenon continued to intensify. Independent consultants would deploy hydroacoustic imaging systems and install additional pressure transducers throughout the structure. Their mission would be urgent, distinguishing between external seepage entering through natural fractures and internal piping already weakening the dam from within. But science moves slowly. Water does not. The fundamental question in such a scenario would remain unanswered. Would this be a geological miracle, an unexpected replenishment from ancient aquifers that could help California through chronic droughts? Or would it be the precursor to catastrophic failure, a warning sign that massive forces were destabilizing the foundation of the state's most critical dam? In the absence of answers, speculation would fill the void. Some might propose hollow earth water pockets, massive cavities in the crust collapsing under immense weight. Others could suggest volcanic pipe hypotheses, heat signatures indicating magma acting as a piston forcing groundwater upward. Still others would whisper about human drilling accidents or construction anomalies. The truth would remain unknown, and perhaps unknowable, at least in time to act. What scientists do know, based on decades of research, is this: Deep aquifer systems exist throughout California's geology. Chemical signatures can definitively identify water that has spent millennia underground. Microquakes along fault systems can open fluid pathways. Internal pressure changes within dam structures create measurable stress responses. Acoustic emissions reveal when embankments are under strain. What such a scenario would leave unknown is almost everything else. Where exactly would water be entering? How long would flow continue? How large would the underground reservoir be? What would happen to the dam if pressure continued building from below? The limits of current subsurface imaging technology mean these questions might not be answered until any crisis resolved itself, one way or another. Humanity has always believed it could tame nature with concrete and engineering. We have built monuments to our confidence across every river, every fault line, every restless landscape on Earth. For decades, those monuments have held. But beneath reservoirs like Oroville, forces older than civilization exist. Water that fell as rain before humans existed moves through deep rock formations, following pathways we have never fully mapped, capable of emerging where we least expect. The dam stands 770 feet tall. Below it, 27 million people depend on flows that sustain their cities and farms. Above it, a lake holds water whose behavior we assume we understand. This scenario asks a question that applies to every major dam on Earth. Would anyone recognize the final warning before it was too late?